This video explain a welded truss is to be made from grade 300 single equal angles. Design member AB. So we need to design member AB to resist the tensile force N 180 kilonewton. So I think this is the internal force in the members. If you do the for this truss case, if you do the section method or the joint methods, you are able to find this 180 kilonewton is the internal axial force, that is tensile force. Now this one has this is done the welding. Equal angles should be welded on the one leg. So if you have a equal angles, for examples, if I have a equal angles here and only the one legs is welded, so let's say only this legs is welded, that's what it means. Now it has a Fy value 320 megapascals because it has a grade 300. So we take 320 megapascals and 440 megapascal. That is coming from one steel table. So for any equal angles, on page number 22, we have a 320 megapascals, and for 300 and for yield strength for 300 grades, we have 440 megapascal is your ultimate strength or tensile strength. So first of all, we need to find these sections. So 5 NT equal to this design 180. So NT is a tensile capacity is equal to N star over 5. So 180 over 0.9, it's give us 200 kilonewtons. So we have a nominal section capacity of the tensile members. Let's say the section is failing by yielding, and I think in the Australian standard it has given the equations for yielding in the clause 7.2 on page number 93. We have a AG times Fy. So we need to find the gross area. So NT over Fy, so 200 times 1000 because we're converting into Newton, divided by Fy 320, that we take it here. So we have a gross area of 620 millimeters square. So we need to find the equal angles that will have a area greater than 625 millimeters square. Now let's go here and we can find the gross area. So we need to find the gross area which is greater than 625. So on here we have a gross area greater than 625. It will give us, so 625, so 628 millimeter square. It has a 55.6 EA. So we are just taking that 628 millimeter square, that equal angles that we are just taking it from here, which is 628 millimeter square. So we are trying this 55.6 EA. That is here. Gross area is 628. Yield strength is 320, 440 megapascals, as you can see here on the page over on page number 22. On page number 22 we have 55.6 EA, and you have a 320 and 440 megapascals. So NT is the minimum of yield and fractures. That both equations are given here. So we should take the minimum value of between these two. That is the NT. One for yielding, another one for fracture. Now for yielding is AG times Fy. That is again taken from the page number 93, and AG times Fy. So that is 628 gross area. That is taken from one steel tables on page number 21. We have 55 we have a 55.6 EA. We have 628 millimeters square is the gross area. So 628 times 320, that is coming from one steel table, and we have a 906 divided by thousands, that is rounding of 201 kilonewtons. Now for fractures, we have 0.85 KT AN FU. That is coming from this from page number 93. We have 0.85 KT AN FU. Now these factors KT, that is the correction factors. Now for correction factors, we should use table 7.3.2 on page number 95. We have equal angle and is welded with the one legs that is given in the conditions. So 0.75 for unequal angles, but we have equal angle, so we take it 0.85 in this case. So KT equal to 0.85. KT equal to 0.85. Net area is gross area. We don't have any holes or anything, so we can take it AN is equal to gross area 628. Fractures is 440. That is on the page number 22. On equal angles, we have a tensile strength Fu is given 440 megapascals. So that is 440 give us this Newton, 200 kilonewtons dividing by 1000. So we need to take the minimum of yielding and fractures. So 201 that we get it from yielding and 200 from fracture, so 200 kilonewtons. So multiplying by the safety factor 0.9 give us 180 kilonewtons. Now trial section is okay because 180 kilonewtons match 180 kilo. We should get the capacity more than what we want to target. So in that case it's okay, but in the reality I suggest that we should suggest that 55.6 EA is very close to the targeted value. So I should suggest that we should go one above, which is 65 times 5 EA. So that would be more safe. So in that case we might take the 65 5 EA for to be on the safe side, so which have a little bit higher capacity. We can repeat the quick procedures here. We can just do these two quick calculations for these cross sections, and it should have a capacity more than 180 kilonewton. That should be safe side. Thank you very much.